Hear? Actually, turn up your audio a little bit, see if you can hear. Can you hear? Cool. Oh, true. That.
Maybe just share.
Is that? Yeah. Okay, cool.
So let me see.
See if you can see if when I switch here. Wait. Oh, wait, hold on. Is it working? What can you see? I think it is recording, right? It is recording.
Yeah, I think it's recording.
Can you see that? What? No? Oh, you can? Okay, let me see. How do I start? Huh? Yes. I think ELSOC will upload it. Where? YouTube. I'm a YouTuber now. I'm like Khan Academy, bro. I don't want to say it. I can say it. You can say it. It rhymes with ink. Okay, now I'm very stressed. That's fine. Actually, so chill. Even in that, like, actually, so that's. If they ask a question I don't know how to answer, help me. Yeah. All right. Hey guys. So we're just gonna start. Yeah. Welcome to the 2141 Midterm Crash Course. There is a lot of people here. I am very nervous right now. Thank you. So what I'm gonna do is I'm gonna go through one of the past years. I know there's solutions to it, but I'm just gonna kind of do it in front of you, and then you can kind of see the thought process and also just how to do some of the questions. I am also going to just try to cover some stuff that I think is like kind of important that you would probably need to use. I reckon I can start with that. And then, oh yeah, the past year that we're doing is, I think this is version 7, 2023 on your. It's F14. Yeah, and then what else? Depending how we go on time, I might do an extra question, depending on what people want. Probably design or Verilog, I'm guessing. Like, how are you guys with base conversion? Good? Good, bad, meh. Okay, fair enough. Okay, cool. So, is there someone else? Okay, so I guess we can start. What I'm gonna do first is I'm gonna go through some of the more useful Boolean algebra identities that you're gonna find. Like, they'll probably be really useful to remember some of these. Some of it is kind of intuitive, but yeah, some of them, it's honestly how I do it is I just memorize it. Because there's a few that once you memorize like maybe 3 or 4, the rest will kind of come naturally, and I'll show you. So I guess one of the first ones is this one, x plus yz equals x plus y, and then x plus z. That one's really good. And then this. So some of the dual ones are also really useful. So with these ones, so these two are equals of each other. So with these ones, if you know one, you will know the other one. All you have to do is just kind of switch all the signs. So all the ors become ands, and the ands become ors. And then so if you know one, you can kind of derive the other one just by knowing the duality function. And then this one is also really good. Very useful, and then that has the dual that. Just to this. Oh. I've seen you before. Okay, anyway. This one's also really useful one, and then that also has a dual, which those two. And then, oh, there's a really long one, but that one, I've never used it in the exam at all, but who knows, one day it might show up and might be actually useful. It's this one, or that one will just end up being and then this one also has the dual, which that's not negative. Cool. So yeah, and then so those are some useful ones. Some other useful ones is probably your XORs and XNORs. So XOR. Also, I'm sorry for the mess that I'm just writing things everywhere. So XOR, you have XOR with, let's say, 5. That will just be X bar Y plus X Y bar. So XORs are only true if both of the inputs are different from one another. So you can see X bar and Y, those two are different, or X and Y bar. And then XNOR would just be that, which would, oh my god, I have no space, which would be XY and X bar, Y bar. So XNOR, opposite of XORs, where it would only be true if both the inputs are the same. Cool. Is there anything else? That's probably one of the more useful ones. The other ones that are might be kind of intuitive, but very useful for like manipulation and stuff is things like x plus x plus x. So if you want to like factor things out even more, you can add in another element. It won't change the equation. This one also very useful if you want to factor down further, but then you don't have the right things to do so. Sorry, I don't know what's the right word for that. What else? Oh, and then just your x plus x bar equals 1 and x bar equals 0. Those are also very good for factorizing equations. Cool, I think that's it for the identities. Now we can get to a question. Fun time. Cool. So let's see. Consider the Boolean function f, assuming, okay, express the function f. 2141? Yes, you're in the right place. Cool. So express the function as a product of max terms. So first step, does anyone know what we should do? Cool, no response. Okay, so the first, we want to kind of get rid of that XOR there because that's not useful to us. First thing you want to do in these is you get rid of XORs or XNORs if you can, and then also break up some of these complements. So doing that, that would give me F. At, yeah. And let's break some of those ones down. So then we have that breaks down and it turns to that first one. Then breaking the second one down, we would have B. Cool. So now what we can do is try to look for factors. Try to factor some things out. Oh wait. We can break those down. We can break these ones down even further. So then you have C bar. Oh, no, that C. Also, if you guys spot any mistakes, just feel free to let me know. It is recording, right?
Yeah.
Okay. Okay, cool. So now we have that. And then what can we do here? Let's see. Oh, wait. Oh, wait, my bad. No. It's not a factorization question. So yeah, they want product of max terms. So for the max term and midterm questions, just want to expand everything out as much as you can. So A, B bars. You want one? Yes. So just looking at this part here, that part first. So if we expand that out, you get A bar, B, C bar for the first one. And then for the second one, this A bar, C bar, D bar. When you multiply that with C, D bar times C is, does anyone know? When you multiply something with its complement. Yes, exactly. So that part just disappears. And then A bar, D, A bar, B, D bar, multiply with D bar. when you multiply something with itself, it just becomes 1. So then that would just actually. Wait, what am I missing? A bar B. Oh, yeah. Last one. Cool. So that one becomes 0. And then those two just become, well, this just becomes same as that one. So then you can just. Cool. Then F have cool. So then what you can do from here is you would have to make your truth tables. So that works. We have A, B, A. So the easier ones to see in the truth table are the ones with all 4 terms. So for example, A bar, B, C, D bar. So you know that's 0, 1, 1, 0. So that one will be true. And then for the rest of them, like let's say, so for example, the last term there, did I screw up? Did I mess up? Oh, yeah.
Scroll back up. Change the.
What?
Just when you've expanded using.
Wait, hold on. This line or this line? One or two?
That line, yeah, so line 1, BC dash, C dash.
Oh, my bad. Okay,
I should have told you.
that's all good. Okay, so that is that, and then that would mean, oh my god, that means that whole part change. Okay, my bad, guys. It's all good. Oops. That one B, and then wait. That one becomes B. That one becomes A bar, B bar. Then when I expand that out, that becomes A bar, B bar. that becomes A bar, B bar. What else? Cool. A bar. And then that A bar. Cool. Yeah. So that one becomes B bar. That one also becomes just become C. And you would have the first one stays the same. That one becomes that. That one does that. And then cool. So we would have that function is the same, that function is the same, that function is the same. That function is the same. All right, cool. So that one should be right. Yo, guys.
Guys, can you please be quiet? Thank you.
All right, cool. Where was I? Okay, yeah. So the one with 4 terms, it's kind of easy to so like this one here, kind of easy to see where that's true in the truth table. So for the others, you can either expand it out further, or you can kind of do it manually, but that's sometimes a little hard to keep track. So for example, let's take this last term here. So we know that one will be true when A is low, C is high, and D is low. That means B can be either or. B can be either low as well, or it can be like that. So then in that case, you would put those two parts as true. So that would be here and oh yeah, that one's there already covered. So yeah. So you can expand it out further, or you can just keep doing that, and then eventually you'll end up with oh wait a minute, I forgot. Oh yeah, so yeah, this one will just cancel out as well. So, yeah, if you get duplicates, you can just kind of cancel that out. So your truth table would end up looking like going down that path, you would get that. Cool. I think I messed up somewhere. Yeah, okay. Cool. So that's your truth table. And then from here, what are they asking for? Product of max terms. Yeah, so that would just be all your zeros. So then that would be that, and then all the zeros. So that's 2, 2, 3, 4, 6, 7, 9. Yep, 9, 12, 15, 15. And that is part A. Yes, these types of questions will usually take a bit of time. So if you're going to spend most of your time anywhere, probably do it on like the first few questions where you have to draw truth tables and K-maps and stuff. Cool. So next part, simplify the function using K-map and express it as a product of sums, list all prime implicants and essential prime implicants. Cool. K-map. So since they want the product of sum, not the sum of products, so normally how you would do a K-map is you would group all the ones, and that would give you your sum of products. So something like BC plus AB, something like that. But since they want a product of sums, what you would do is you would put down your zeros instead of your ones, and you would start grouping your zeros. So if I do that, that is so 2 and 3. So it's those two. By 4 and 6. Oh, and 7. 9. 12. Wait, 12 is that one. And then 14, 15. Oh, wait, no. What is? What? Oh, yeah, 12. Wait, nope. 1, 2, 3, 4, 5, 6, 7, 8. Oh, yeah, that one. That one. Cool. So then you start grouping your zeros. So you would have that one there, that one there. Then you would have those 4 up here, and those 4 there. And then you just have a single one. Right, yep. And then they're asking you to list all your prime implicants and essential prime implicants. So, oh yeah. So typically if these zeros or ones, so for example, let's take that green square, you would have, it would be A bar and A bar D. Yeah. Wait. B bar. Wait. B D bar. My bad. B D bar. Yeah. So if those zeros or ones, you would get B D bar. But since they're zeros and they're also asking for the product of sums, this would just be, you would basically, this is SOP. So then for product of sum, you would just take your SOP and bar that whole thing. So B bar, that would be cool. So that's the green one, the orange one. So prime implicants would just be, prime implicants would basically be every single one of those squares there. So you would have that green one, which is B bar, D, and then that solitary blue one is A, B bar, D. The pink one is the A bar, yep, A bar C, and the orange one is B C. Oh wait, these would be SOP. So then you convert that, if you want to convert those to POS, you would get so your prime implicants would be this one up here and these three down here. Move this up. Cool. And then they're also asking for your essential prime implicants. What? So essential prime implicants are, okay, how do I word this? It's essential if there's a 1, or like in this case a 0, that's not covered by any other square. So for example, that would be this solitary blue one, this green one right here, and yeah, that's about it, because this pink one and this orange one. Oh, yeah, there's that one there. Yeah, you're right. Okay, yeah, so it's the orange one. So the pink one wouldn't be. Yeah, so you'd have what? Which two? Oh, yeah. Oh, all of them are essential. Yeah, so in this case, all of them are essential. So yeah. So then you just write the same thing down here. So you can just kind of just do all essential. So in the exam, you can just write that. Cool. Part D is find a new simplified sum of products if don't care functions are added. Cool. So I'm just gonna do it in this same truth table. Actually, I might new page. Be that. Cool. So then we just fill in 1. So since they're asking for, now they're asking for SOP, so then we can fill in 1s. And there is a don't care at 2, 3, and 9. So 2 and 3, these two, turn into X, X's, and 9, this one also. Then we can fill the rest with 1s. And then we can start grouping things again. So you would have these 8 here. And then you can group this entire row here. And that's all, that's basically all you need. They're not asking for every single prime implicant. Yep, so that, and then you can just get your SOP function as, that would be RD plus B. Yep. Oh wait, no. Yep. So that's your final answer for that one. And then last question, E. Yes. So with choosing your rectangles, you want to first find the biggest possible one. Start from there. So the biggest possible one here is, oh yeah, also a common thing that people forget is you can like kind of go across the boundaries. So like that green one there, I'm taking the top and bottom row. So you find the biggest one, which is that 8 there, and then you see what else isn't. So when I had that green one, the only 2 ones that I had left are these 2 in the middle. So, and then you see how big that group can get. And in this case, I can group them down, all 4 of these like that. So then that's how you kind of, you're trying to cover as many ones as possible with as few boxes as possible, if that makes sense. Try to take big boxes and try to get, also remember you only can like group them in like 2s, 4s, 8s. And then if you group 16, if you group the entire thing, you just get 1. Yeah. that make sense? Yes. Oh yeah, so for don't cares, that basically means they can either act as 0 or 1s. So if they help you to group, you can take them into your grouping. But if let's say just for the exercise, like this one is a don't care, you can kind of ignore that one there because it wouldn't help you to make a bigger group. Yeah. Cool. Yep. And then the last part, use your simplified expression from B. Draw the logic circuit using NOR gates. Okay, cool. So NOR only implementation. I might do this one. Oh, is there a gate info cost question? Yeah. Oh, my bad. So that's part C. I'm just gonna do that down here. Cool. So gate input costs of your function from B. Oh, cool. That's perfect. So B, I'm just gonna write it again down here. B, your function is. Yes, did you have a question? Did someone have a question? I thought I saw someone's hand raised. My bad. Okay. Cool. So gate input costs. So in this thing, we have 4 terms. So that's just 1, 2, 3, 4. Literals, we have, well, we have 1 for B, 1 for C. Oh, we have 1 for A, 1 for D. So we have all 4 of them. So complements, my bad. Complements, you have 4 complements. You only count once because if you implement it, you're just gonna put it through one inverter at the start, and then you can take that to go to multiple wherever you need. So complements only count 1 time. So you have 4 complements. And then with literals, you have 10. Yeah, so literals, that one's kind of straightforward. You just count literally every single one. 10 literals. And then so your data input cost is cool. And then part D, I mean the last part D, is implementing that as NOR only. So I'll write that down here again. So yeah, the easiest way to do this is how you see it in solutions where they just do it normally and then they add the little bubbles and then they convert it. So you would have to draw it twice. Or you could, I think in the lecture notes, there were the universal gates that look like, they just kind of look like that. So for NOR only, this would be an AND. But then some of these gates would cancel out when you do the implementation. So then this isn't actually that efficient of a way to do it. Cool. So if I do this as NOR only, I would have this. Oh yeah, also assume no complement of literals. So I need 4 of those. And 4 of those will go into an AND gate. Do that. Actually, don't do that. Or just go into an AND gate, and then oh yeah, what you can do as well in the exam, just to make your life kind of easier, is you can, let's say you want A, you can do that, that, do something like that, and then you do that for A, B, C, and D, And then so at the inputs here, you can just literally just write that. Yeah. This just makes it so. Oh wait, this one should be 4. This just makes it so you don't have to like draw a bunch of lines everywhere and then kind of get yourself confused. You can just separate up the circuit just to make your life a little easier. Cool. So to turn this into a NOR only implementation, what you do is for the OR gates, you put a little circle there. And for the AND gate, put little circles there. And then if they cancel out, that's great, perfect. If they don't cancel out, if there's an extra bubble somewhere here, you would have to add a NOR gate inverter, which would look that. Cool. So if I turn this into all NOR gates, you just have, well, actually, that, 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 and then for the inverters, you can do at the side. You can just do a bar there, a there. And then you just do this 4 times for every single input, and then you put your same thing, same deal. Oh, this one's 4. Cool. Yes.
I'm pretty sure that is better than it's an game. Have one like any right? The output is still. I'm thinking like the other two will count. Oh no, I'm thinking X no.
Now you got me doubting myself. Okay, let's. Okay, so if A is 0, that would turn. Okay, he said I'm correct. Yeah.
I was thinking X.
Okay, yeah. Cool. Cool. So that is the first question, I think. I think that's the entire first question. Cool. All right, moving on. Question 2. Oh, yeah. Yeah, so the structure will be kind of similar to what you saw in the past years. The first question will be something like what we just did. Then there'll probably be one question on like base conversion and like 2's complement arithmetic. Then there should usually be one design question where you have to draw like 4 different K-maps and implement the circuit. And then there will usually be like, a simplification question and a very long question. So yeah, expect one of each. For the design question, most probably, do not quote me on this if it doesn't come up in your exam, but most probably it will either be a decoder or a multiplexer. They want you to implement it with a decoder or a multiplexer. So yeah, keep that in mind. Might be very useful to study. Cool. So, question 2. Base conversion. So decimal numbers x -107.26 and y 59.17 converted to base 5. Cool. So for the non-decimal part, was it integer? Yeah, the integer part. What you would do for base 5 conversion is, or any other base, honestly, is you would, well, I like to do it like this. 107. Cool. So 107 divided by 5 is 21. Remainder of 2. So then you put your remainders at the side. 21 divided by 5 is 4 remainder of 1. Cool. And then that's it. that's where you stop. And then so you would take the numbers, your MSB is that one there, the least significant is that one there, so that way. Cool. And then, so for the decimal part, you just take 0.26 times 5, which is, I'm just gonna write down what I see. And then you ignore the 1, you take 0.3. Oh, yes. If they don't mention how many decimal places they want, do it up to maybe about 4, just to be safe. Yeah. So 0.3 times 5 is 1.5. 1.5, yeah. 5 times 5 is 2.5. Then, well, you have that again. Yeah. They'll probably just keep on going forever. So then your decimal places, you would take this row of numbers right here. Oh, and they go down. So then x would basically be negative 412.12. Cool. And then now we do y. Y is 59.7. What's that divided by 5? 11? 4, and then 2 and 1. Yeah, okay, cool. And then the decimal was 0.17. 5 is 5. 0.85. 5, you would get 4.25. And then you can 2.25 times 5 is 1.25. And yeah, you can see it kind of repeats again. Yep. So again, that way for your integer part, and then this part for your decimals and going down by the 214.0411. Cool. Find part B, find the equivalent sine 2's complement. Oh my god, I'm so sorry. That's napalm death. Okay, cool. So part B, find the equivalent sine 2's complement using 8 bits to represent the integer and the fractional part. Okay, this is going to be pain to do. But what you would do is, you can take your similar like kind of method where you would just divide by 2 until you can't divide anymore. And then same with the fractional bit. Since they're asking for 8 bits each side, so the fractional bit, you would have to multiply it like 8 times until you get 8 in the fractions. Do you guys want to see me do that? Yes? Fine, I'll do it for one of the numbers. But I think after a while, it's going to get kind of repetitive, and I assume you guys will know what to do. What the heck? Cool. Cool. So help me do this math. I need you guys to start telling me numbers. 26. This is 0, right? What? Yes, but you're dividing it by 2. So then you have 6 with a remainder of 1. You're basically taking, you're taking this middle row of numbers, dividing it by 2, and then putting the remainder on the right-hand side. Yes. Yes, and then there's a 1 there. Yes. Cool. So how many numbers is that? 1, 2, 3, 4, 5, 6, 7. So for 8 bits in the integer part, so this one you'd have 110 and 1011. So for 8 bits, just add a 0, pop a 0 in front, and that gives you your 8 bits. And then the decimal part of that is 0.26. So since binary is base 2, so you would multiply by 2. And then doing that would be 52 times 2, that gives you 0.04. Then 0.04 times 2, 2.08. You guys really want to see me do this all the way through? Okay, fine, fair enough. Times 2, 0.16. 0.16 times 2 equals 0.32. How many do I have? 0.32 times 2 is 0.64. 1, 2, 3, 4, 5, 6. 0.64 times 2 is 1.28. Right? Yeah. 0.56. Is that right? Did I do the math right? Yep, that looks right. So then your decimal part would be 0.1000010. Cool. So that is x. And then, so they want it in 2's complement. So what you would need to do is for 2's complement, you just do it to it. You just do it as well. Nothing changes. I'll show you. Yeah. So for 2's complement, you invert all the bits, and then you plus 1. So for 2's complement of x, have, if I invert all the bits, I'd have 1 0 0 1 0 1 0 0 dot 1 0 1 1 1 0 1. And then you would add a 1 just to the end right there. Cool. So then you add 1. That would give you 0 1 1. Yep. 1 1 1 0 1 dot. Then that whole part doesn't change. Cool. So that is your 2's complement of x. That's your final answer for x right there. Cool. And then for y, what is y? Y is 59.17. Cool. 59 divided by 2 is 29. Divided by 2 is 14. Remainder of 1. Then that's a 7 remainder of 0. That's a 3 remainder of 1. And then that's just 1 remainder of 1. Cool. So we have 1 0 1 1. And we have 2 1s there. So you smack 2 zeros in front of that, and that gives you your integer part. Okay, don't do the decimals. Okay, thank you. Okay, so then you would have your decimals. If you do the same thing again, you would eventually get 0 0 1 0 and 1 0 1 1. Bye. Cool. So that is your y. I think y was a positive number, right? Yes, y was a positive number. Cool. So then part C. Let me just put x down here as well. So if your number is positive, the 2's complement would be exactly the same as just your regular binary number. So if it's a positive number, you don't have to do the thing where you switch all the bits and then like add a 1 to it, because it'll be the same. But you have to do it for the next part anyway, so I'm just going to do it also. Let me move this here. So the 2's complement of that is 0 0 0 1 0 1 0 0. You add 1. So that 1 0 0. Yeah. And then everything else stays the same. Cool. So that's your y. 2's complement, and then your x will. Cool. The next part, they're asking you to perform 2's complement subtraction to find the result of x minus y. Cool. So what's that, like part D, part C? So x minus y is x plus negative y. So since we have x right here, 2's complement, and we have y right here, 2's complement, we can just add those together, and that would give you your subtraction, this basically. So if I do that, x 1 0 0 1 0 1 0 0 1 1 0 y 1 1 and then add. Cool. So if you add that, you would get 1 1 that's there, 0 1 there. 1 plus 1 plus 1 is 11. And then you just keep going. Oh. Is that right? Oh wait, I think I messed up somewhere.
Yeah.
Where did I mess up?
Second place.
What at the decimal? Oh shoot, yeah. Wait,
The one right is the
wait for y or x?
oh.
Okay, wait, no, that's correct. Okay, hold on. Let me just double check real quick. Of x or y? X? Oh, the answer. Oh, 3 to the left of the decimal. 1, 2, 3.
That should be the 0.
Oh, yeah. So that's 0. Is that right now? Oh, this one should also be a 0. 0 1 0 1 1 0 0 1 1 0 0 1 0 0 1 1. Okay, yeah, that's correct. Cool. So, part D, they're asking you for your status flags. So, for negative, for n, so wait, you have 4 n z n c d. For n negative, that one's really easy. You just look at this one right here. So if that's a 0, wait. I think the solutions are wrong.
Yeah,
The solutions are wrong, yeah. Yeah, so for negative, you look at that one there. So then this one is just 0. For your carry, you look at that one there. If there's a 1 there, you put 1. Overflow, I'll get to that later. And then for your 0, well, if your number is clearly not a 0, it's not a 0, so that's false. So for overflow, what you can do is carry n x or carry n minus 1. This basically means is this value the same as the carry value here? Well, there's no carry value here, so that's 0. So is this value the same as this value? Yes or no? So in this case, no, it is not the same. So then if you since it's an XOR function, that one would be what? Make sense? Cool. Any questions for this part? Oh yeah, you can take quickly.
So
Yes.
just scroll up to question D again. I didn't actually.
Which one?
Question D.
D. Oh, yeah. D is, yeah, so for the status flags. So status flags are just the V, N, Z, and C thing. So can we go through that again? Kind of explain how the flags work. You sure? You sure? Okay, yes.
Why do you end here?
Yep, so N is 0. N is, so for the value of N, you would basically look at this value right here. And if it's a 0, it's a 0. If it's a 1, it's a 1. You basically ignore the carry. Yes, you ignore the carry. Yes. You look at your most significant one, ignoring the carry. No. The carry is a result of computers not having space. Cool. All right. So the next part. Yes, a design question. Fun. Cool. So let's see. Oops. Design a computational logic circuit that adds a decimal number 5 to a 4-bit BCD input. There are 4 inputs. Well, you guys can read the question. So draw the truth table. So A, B, C, D as your inputs, and then W, X, Y, Z outputs. Cool. So then you would do this thing again. 1, 2, 3. 6, 7, 8. 1, 2, 3, 4. Cool. Okay, so it says ABCD is equal to WXYZ plus 5 is the result is less than 10. The result is 10 or above. ABCD is 1111. Cool. So what that basically means is add 5 to the input. So 0 add 5, you would have 5. So 5 is just 0, 1, 0, 1. Add 5, and if it's add 5 to the input, but if it's more than 10, make it 15. You'll see what I mean. So 0 plus 5 is 5, that's less than 10, so that's 1. 5 plus 1 is 6, so that one is less than 10, so that becomes what the root is. 5 plus 2 is 7. 5 plus 3 is 8. 5 plus 9. Oh, wait, no, 5 plus 4 is 9. And then 5 plus 5 is 10. And it says, if it's less than 10, if it's 10 or above, it's just 1, 1, 1, 1. That one becomes 1, 1, 1, 1. 5 plus 6, 1, 1, 1, 1. That one's also 1, 1, 1, 1. 1, 1, 1, 1, 1, 1. Okay, I'm going to stop here. What do you guys think it would be for 1010? You say it's 1111. Who says it's not that? The fact that I'm asking you this question. So if you look back at the question, it says 4-bit BCD input. So remember, BCD is binary coded decimal. So BCD is not the same as just binary. So binary, you can represent as many numbers as you want. BCD is only for 0 to 9. So that input there, 1010 at 10, that input will never happen. So then your output would just be X. Because since, yeah, that's why you use X's in truth tables, is when your input can never happen. So those ones, every single one of those would be X. This is also kind of important to remember. Cool. Now we have to draw for part B, simplified sum of products, and it's 10 marks. They're basically asking you to draw 4 K-maps. So this is going to be pain, but we do it anyway. Why? Because we're electrical engineers and we love pain. I'm just going to copy this 4 times. Cool. So for K-maps, what you would do is, oh wait, I just realized I switched these around. Cool. So for K-maps, what you would do is you would make one for basically each bit of your output. So this one will be for A, this one will be for B, this one will be for C, B for D. Cool. And we can see that A is 1 at every single point past like 3 onwards, basically. Wait, no, 4 onwards. 3, 4, 3, 3 onwards, 3. So you would just, so for A, that's 0, 2, that's 3. And then those ones become 1. And then 8 and 9. And then everything else becomes X. Cool. And then for B, you would have 1 at 0, 1, and 2. Oh, wait, no. The only zeros you would have is at 3 and 4. So ignoring 3 and 4, so 0, 1, 2, that's 3, 4, 5, 6, 7. Then those can be X's, so 1s. Cool, so that's B. C, you have zeros at 0, 3, and 4. So ignoring that one, 0, 1, 2, 3. X, 1, X. And for D, you have zeros at 1 and 3. Cool, so 3. One would be cool. Okay, now we start grouping things. Okay, so you can group, let's start off with that 8 in the middle. So you have that 8 there, and then we have to deal with that bottom row, and we can group that as 8 as well. And then we have that solitary one, which we can group down as 4. Sense? Cool. And then that expression would be, so if you look at this square, that one is B. Here, that one is 8. This one here is B. So you have 8, B. Flip the inputs and outputs. Oh, I did. Damn, sorry. Those are W, X, Y, and Z. But so W, X. And then for B, again, start with the biggest grouping. So you have this giant grouping of 8 down here. And then what you do is, oh yeah, the one that a lot of people miss is the fact that you can group the corners like so. So you can do that. And then you have, I'm gonna use a different color just because it makes it not as messy. You have this group of 4s right here, and that one going down there. And I think that should cover all the ones. Yep, cool. So the one at the corners, that one would be, actually, I'm gonna start with the green one. The green one would be same as before, that's just W. That purple one going down, this one, that would be Y bar Z. This other purple one, that would be X, Y. And then the 4 orange ones at the corner, that would be X bar, Z bar. Cool. That's right. Is that right? Yeah, that looks about right. Cool. And then for C, group that one, start with the biggest one again. And then you have this one down here, that one down there. And then this one in the middle, you can take either, you can either do that or you can do that. The choice is yours, but do not include both of those. You either include only the orange one or the pink one, because if you include both of them, they'll somehow cancel out, but you know, it won't be the most simplified expression you can get. So yeah, I'm gonna go with the pink one. Why not? So that green one again, that would be W. The purple one, the 2 purple ones going down, that would be Y bar Z and Y Z bar. And then that pink one would be X Z. Yeah, the orange one, I'm just gonna put it here. That orange one would have been XY. So you can put either or, XZ or XY, do not put both. Okay, cool. And then the last one, again, you have that big grouping of ones there, that 8 there. You have this other 8 here. And then you can group those for, I use a different color for that. You can group these 4 in the corners. Cool. So you have, again, you have X, W, X is this one, W is that one. And then the ones in the corner, that one is X bar Z, if I'm remembering correctly. Yeah. X bar Z bar. Yeah. Cool. So that is your answer. These 4 is your answers for part B, basically.
Eight.
Oh, wait, true. Good point. I missed that one. Yeah. Oops. Yeah, sorry guys. Sorry for all the hiccups. It's been a while since I've done this. It's been about a year and a half. You guys will get used to it. Cool. And then that one is, that purple one is Z bar. Yeah, on Z bar. Cool. And then these 4, that's your answers for A, B, C, and D. And then last part C is implement A, B, C, and D with a 4 to 16 decoder and the minimum. Okay, you can basically ignore this part here. That part, you can ignore what that says. Clear. And do not assume that complements are available. Cool. Bye. Cool. So what we can do for decoder questions, it makes it easier if you put it in the like this format, the sum of minterms. So for A, if you look at the truth table, the sum of minterms would be 3, 4, 5, 6, 7, 8, 9. So you can just put that there. Nine, and then you do the same for B, C, and D. Just count which positions where the ones are, basically. So for B, it would be 0, 1, 2, 5, 6, 7, 8, 9. You can ignore all the x's. Do not count the x's as part of this. So for B, it would be 0, 1, 2, and 5, 6, 7, 8, 9. C would be 1, 2, 5, 6, 8, 9. D 0, 6, 8, 9. Cool. So I assume you guys know how a decoder works. Do you want me to go through how it works? Who wants me to go through how it works? One person? Okay, you know what? I'll go through how it works. Okay, so a decoder is, I'm gonna explain it with a 2 to 4 decoder, and then for 4 to 16, it'll just, that same idea will just expand upwards. So let's say we have a decoder, and this is 2, 4, which means 2 inputs, 2 outputs. I assume you all did this in lab this week. So for a 2 input decoder, there are only 4 possible combinations of inputs we can get. A and B can be 0, 0, 1, 1, 0, 1, 1. So how I think, this is just for me personally, how I like to think about how a decoder works is, oh wait, let me just name these outputs as x0, x1, 2, x3. So I like to think as a decoder like a, think of these inputs as your passwords to a system. You have your passwords to a system. Oh wait, no, think of it as a key. You have 4 different keys, but those keys can only access 1 door each. Does that make sense? So for 0, 0, this quote unquote key will access output x0 because, well, this in binary is, well, if you convert this to decimal, that's a 0. So it's output 0. Same with the next one. So the next one, your key number 1, that accesses door 1. Key number 2 accesses door 2, and key number 3 accesses door number 3. Does that make sense? Who still does not quite get it? All clear? Nice. Cool. So yeah, think of it as, yes.
It's a bit output.
Yeah, yes.
So like X0.
Well, okay, it's not a 4-bit output in a
It's
way.
like a completely unique key.
Yes, it's like the key opens a door, and it's like a key. Okay, you know how in movies, there's like the nuclear, when they want to activate the nuclear system, they put in a key and they turn it. It's like a nuclear activation system. You put in the key, you turn it, it activates exit. Like you put in key 0, You put it, if you input X00 into here, it will activate X0. It's just like a key and an activation system. And then the inputs, whatever your input is, like this is binary numbers, right? It's just 0, 1, 2, and 3. Those will just correspond to whatever outputs they activate.
So you can have a 2 to 3 decoder, but one of those keys will be in a side. Right?
Well, technically you can, but also you can just have a 2 to 4 decoder and just not use one of them. But which is what? Okay, so remember, you guys did in the lab, you guys built a 4 to 16 decoder, right? And then at the end, you guys had to connect some of the outputs to OR gates. But not every single one of those were connected to OR gates, right?
Yeah.
Same thing. If you want a 2 to 3, you just don't connect one of them. Yeah. Yes. Jonathan, do you know? Do you know where decoders? I think they're using computers, if I'm not mistaken, right? Like CPUs, yeah. If you want to, like, yeah, that sort of stuff. What else? What else are decoders used for?
To convert analog signals.
Ah, yes, you can convert analog signals to digital with decoders, apparently. I don't know. I haven't got that far in my degree. I don't know what decoders are for you. Yes. Yes. Yes, exactly. Which is why, if you remember in your labs today, well, not today, or like whenever you did your labs this week, you have like, okay, you had like something like that, right? Equals. And then the next ones would be the ones kind of travel down diagonally. Right? So these bits are kind of this one right here. That is X0, this is X1, this is X2, this is X3. That's how that works. Does that make sense? Yes. So it kind of like take the value and you turn it on its side. Yeah. And then those will correspond to those outputs. Make sense? All good? Cool. That is probably the best explanation I've done today. Okay, cool. Yes, so they want you to implement this with a 4 to 16 decoder. Again, what you can do to make your life easier is you don't have to like connect everything like together. You can draw for a 4 to 16 decoder. What you do is you can just draw a square. Oh, why is that grayed out? Never mind, it's fine. And then you can just write 4 to 16 decoder. Just label your things. Like if you're just drawing squares, just label them so the examiner knows what it is. And then you would have your 4 inputs, which is W, X, Y, and Z. And then so you'd have 16 decoder outputs here. You don't have to draw all 16 things there. What you can basically do is, so let's start with A, right? So A is only true at 3, 4, 5, 6, 7, 8, and 9. Those will correspond to your decoder outputs. So basically, if you take, what you'd have to do is like, this is very similar to your lab that you did this week. So for A, how should I do this? OR gate, and then A. So what you can do is, so you only want it to activate at 3, 4, 5, 6, 7, 8, 9. So you can just draw 3, 4, 5, 6, 7, 8. Oh, I have no space. 9, sure. And then just write 3, 4, 5, 6, 7, 8, 9. You can just do that, and that will basically be your answer for this part. If they ask you to draw a decoder, you're basically connecting. These are all basically your decoder outputs, and you want to connect them to the OR gates. So then for B, you would have 0, 1, 2, 5, 6, 7. Oh my God, I have no space. 8. Okay, 0, 1, 2, 5, 6, 7, 8, 9. That's B. C is 1, 2, 5, 6, 7, 8, 9. 2, 5, 6, 7, 9. And then D is 0, 2, 4, 5, 6, 7, 8, 9. That's not an output. 0, 2, 4, 5, 6, 7, 8, 9. Obviously draw it better and neater in the exam. But yes. What'd you get? What'd you say? Yes. I mean, as long as they can kind of see your numbers. I feel like if they see that, they might actually mark you full marks. They'll just be kind of pissed at you. They'll just, yeah, they might hate you. Okay. So does this part make sense to everyone? Does anyone have any questions?
So they would usually expect us to draw every single line.
No. You don't have to draw every single line. You can do it like this.
Oh,
Because drawing every single line is hell and pain.
yeah, the guy with mark and then
Yeah. It'll be like worse for him to mark actually. So doing this will make your life and their life easier. Yes. Yes, because your midterms is basically the same as a sum of products, right? So that's why you are like 3. The product at 3 is like 0, 0, W bar, X bar, Y, Z. That is the product because they're all multiplied together and then you're adding every single one of those. Make sense? Yes. Yes, that is the entire answer. You just your answer is basically wait, let me see what they asked. Exactly. Implement. Yeah. So your answer is kind of just this bottom part right here. I assume with all exams, like every single exam, if you mess up the first part, marks do get carried over. You might maybe lose I want to say 2 or 3 marks. Yeah, but if you kind of get this overall thing, you should get a good portion of the marks. Yes. But also note that with 2141, this happened to me in the midterm last year. With the first question, I screwed up very early on, and then when I got to part E of the question, I realized oh crap, I can't do the question because I screwed up. So I had to redo the entire part, and then so sometimes that happens. If that happens to you, do not be like me. Do not do the entire question again. Probably don't do that unless you are really confident that you have enough time. Because yeah, and then I ended up not doing an entire question because I ran out of time completely. So yeah, that's just a little tip there. Yes, with 2141, if you mess up early on and you get to later stages, some things might get weird. Because for example, if you screw up here, if you screw up this truth table, your K-maps are gonna be very weird and very hard to minimize. So then you will kind of realize that something is wrong. Because if you read the whole question and you know they want you to implement the decoder, but this is kind of difficult to simplify, probably something's wrong somewhere. Yes. All good? Cool. All right, what's next? Oh my God, everyone's favorite part and my least favorite part. Simplification. This is where I screwed up in the beginning. So no promises that I don't screw up again somewhere here. But let's see what happens. Okay. Use algebraic manipulation. Actually, I'm gonna make this smaller. You guys can see that, right? Okay, you know what? Fine. I won't make it smaller. Okay, use algebraic manipulation to optimize f to a simplified sum of product form. Cool. So, similar to how we started, what you want to do is first you want to break up your complements, like your double bars. So you want to break that up. You want to, oh, that's the only one. You want to break up complements, and once kind of like at every single step, once you do one thing, see if you can like cancel things out. So after you break the complement, see if there's anything you can cancel out, and then if there's nothing you can do, you start expanding things, and then I'm just gonna start doing it, and then you'll see. Okay, so F is breaking that up. We have B, well, that would be B double bar plus D double bar. So that would just be B plus D. And you have A C bar plus, I'm not gonna expand this in yet, just because something might cancel out later on. And then, oh my God. And then that A, you can probably multiply in and that. Okay, cool. Let's see what we can do. Oh my God, I hate this. There's nothing we can do. Okay, that means we have to start expanding things even more. Oh, there's something. Okay, that's your first thing. That's the first thing right here. So A, that one, when you expand that in, that becomes A that. Then the other one also becomes cool. So we can do things with that later on. But I'm just gonna write down the rest of the things first. Okay, that's that. Cool. So E times D bar. What does that become? Yes, very good. So this whole thing just becomes 0. Bye bye. Cool. And then that whole thing becomes 0, and then this one. Okay, I see. If you expand out this section, you have A bar, B plus A bar, B. Oh, you guys are back. Cool. Plus A, B, C plus A, C, D. And then I'm just gonna expand that out. Cool. And then where was it? This part also becomes 0 for the same reason that one became 0. This one also becomes 0. And then I'm just gonna rewrite it down here. Cool. Let's see what we can do from here. What? Yes. You guys have something? Yes. Nice. Good find. Okay, let's do it one at a time. Let's do it one at a time. So I'm gonna write ABC there. Then you can take AC and then C plus C bar. This whole part becomes 1. So then, that kind of does its thing. Then you have, oh, you can do that again. That one becomes 1. Ooh, and then you can do it one more time. I think that should be it. Oh wait, actually, there's one more thing we can do actually. So now you have B plus BC, and that becomes nice. So then you have, I'm just gonna write it here. Simplified. Heck yeah. Actually helps. Cool. So that's that. Yeah. So that is that. And then what is part 2? Using the principle of duality, find the product of some form of the complement of F. That one's really easy. What you have to do for part B is they just kind of want you to do that and then De Morgan that. So you would have and then that can break down in R. That's it. Cool. And then for part C, C is implement F with 3 state buffers with C and D applied at the enables and cool, 3 state buffer. Okay, so this is kind of another design question. For me, what I find is the easiest way to do this is draw a K-map. So I'm just gonna write F up here again. What was F? F was, what was F? AD. So cool. So obviously we don't have a truth table, so it's a bit hard to fill up this K-map. And we don't have the sum of minterms. So how do we fill up this K-map? Well, we kind of have to do it. It's kind of a shortcut, but it can get very confusing very quickly. So, you know, statement, so for F, you know that will be high whenever, so I'm gonna write F high at, so A and D have to be high, or B high. So you find the parts, you find the places in the K-map where these 2 statements are true. So where A and D would be high is, I'm gonna do it in red. I'm gonna do this one in red. So A and D is high. Well, A is high there, and D is high there. So that one, A and D are high. A and D are also high here, right? That one's A, that one's D. And then A and D are also high here. And that's it, I think. And then B is high at this entire row, basically. So you have 1, 2, 3, 4. And B is also high at this entire row. So one of those 2 covered. And that's it. That is how you do that. It's kind of a shortcut, but it can get very confusing if your expression is a little bit longer. So yeah. Cool. So the question asks for tri-state buffer with C and D at the enable. So similar to a multiplexer question, if let's say, well, For tri-state buffer, you have an enable. For multiplexers, you have your select lines. You would have to draw the squares in the K-maps, but the way you draw the squares will be slightly different. So since they want C and D as enables, you group the ones. Okay. What you can do is imagine that there's a brick wall here. These are brick walls, and you can't group it across those walls. So what you would have to do is group these, those, group those, and those. So then these groupings become your what you would input into the enable for the tri-state buffers. So this one would be, that would be B. That one would be, well, these two would be B plus A. Yep. That one would also be B. Cool. And then now we can draw our tri-state buffers. So yeah, again, similar to how if you don't want to like draw a bunch of wires everywhere, what you can do is let's put my tri-state buffer there. And then, so these are your tri-state buffer inputs. So that one would be B. Those, that one would be A plus B, that one would also. Cool. And then you can do for A plus B, you can kind of just draw an OR gate at the side here. And do that, and then just write here A plus B. And then now for your buffer enables, it'd basically be you'd have these four up here. So what you can do is that one is C bar D bar. You have C bar D bar. So then what you can do with that is you can just draw your AND gate at the side, and then like, and then you'd have to draw like 4 different versions of this to correspond with each one of this. Does that make sense? Make sense? Make sense? All good? All good? Yep. Cool. All right. The last part, very long question, everyone's favorite. Cool. So rewrite the Verilog using data flow modeling. As a reminder for everyone, data flow modeling is just using your assign statements. So, well, looking at this, you would, since your output is F, what you could basically do is start off just by writing assign F. And then you can do this in 2 stages. You can either do it in just one single assign F statement, or you can do, well, you can see that there's also 2 Y's here, Y0 and Y1. So, never mind. You can also do, assign F and write the whole thing out, or you can do assign Y0 equals not of C. So that is that. And you can do assign Y1 equals B and Y0. Then you can do your final one, assign F equals. I swear I heard something. Y1 or A. Or you can just do it in one single statement, and then that would be B and Whoops. My guy. So it should be A word with B and like that. So you can either do it in one line or you can do it in 3 lines. Either way is correct. Cool. And then for the last one is the same deal. Except for the last one, you would also need to write. So you see how this one it has input A, B, and C and output F. This one is missing that, so you would have to put that in as well. So you'd have to write input. Well, just looking at the names, you can tell A, B, and C is your input. Output Z1, Z2. And then you can do assign Z1. If you want to do it in one line, easiest way is to kind of work backwards. So you can see it's A XOR with F2, and F2 is B. Oh wait, that's not the XOR symbol. What's the XOR symbol in Verilog? Oh yeah, that is XOR. Yes. So so it's B NOR with C. So you can do that. I'll make this square. Cool. And then for Z2, assign Z2 is you have C XOR with F3. F3 is another XOR. So it's B XOR with whatever is F1. So B and C. Cool. Does that make sense? All good? Cool. Which one? That one?
Oh, wait, no,
All good? All good? Cool. We have about like 5 minutes left. Do you guys just have any like general questions? Yes. Any other questions that you want to clarify? What? 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 What did you say? Yeah, yeah.
All right, guys. Everyone give Joe a big round of applause. Thank you. Thank you to everyone who showed up in person and online. We'll be making the recording of this. We'll be posting it to YouTube probably over the weekend, so keep an eye out for that. And yeah, good luck everyone on your midterm next week. We'll probably be putting on a similar one for finals, so keep an eye out for that. All right, thanks guys.